Hey everyone, today I'm excited to present a project on GaitBERT. It's a novel approach for gait recognition by predicting mask frames in video sequences. Gait recognition is a critical task in computer vision, useful for surveillance, security, and health monitoring. So let's deep dive into what we have done. So gait recognition by estimating temporal orders of frames. So what we are doing? So we are basically trying to recognize humans by his walking style. So identifying individual based on their gait or manner of walking is challenging due to variation in appearance, clothing, and occlusion. So traditional methods struggle with these variations, so leading to the need for more advancement in it. So our project aims to improve gait recognition accuracy by predicting mask frames using a UNET architecture, and we are enhancing it using different loss functions. So we know each person have different walking style, and each walking style can be captured from multiple camera views. So from that, so a person walk video contains several frames. So if a person walk from one place to another, then we can capture it from a video, and each video has several frames. So we pick random 50 frames from a video to represent a particular video. And yeah, our data set looks like this. So in the root folder, we have different folders in it, each representing person ID. So a person ID basically represent a particular person exist, and each person have different walking style. So it will divide it into further steps, and each walking style have different camera views in it, starting from 0 degree to 180 degree, and each camera view have different frames in it, which we are representing a video from. You know, we're basically using 3D convolution in this, and we are basically learning get features and embeddings. So how we are approaching it? So we have this dataset KCAB, and the model that we are using over here is UNET. We are using 3D convolution on random mask frames from a particular video. So what we are actually learning is what are there to make a particular walking action, and what variations are there in a walking action. So if we see the part of UNET, the encoder part, so we have given a video. So first of all, we gathered 50 different labels, each representing different person in it, and that basically represent a particular batch. And each batch have 50 frames in it. That is representing a particular video. And in that way, a batch is created. And now we are passing that through the encoder, and we get the embedding of whole batch. That's what we are creating. So what encoder is doing, it's converting higher dimension to lower dimension. Then in between this, we are training this encoder. We are calculating two losses, the triplet loss and the cross entropy loss. So each batch contains these 50 embeddings, basically representing 50 frames of it. That's what we have stacked. So after training the encoder on it, we are reconstructing the image from the decoder. And what we are using to check the whole network is mean squared error. So why we're using 3D convolution? So 3D convolution is a convolution operation using neural network to process three-dimensional data, first of all. And if you begin with a video of an individual represented as a 3D volume or sequence, and those are random portion of these frames are masked, and each frame is initially at 64 cross 64 pixels. So while 2D convolution operates on 2D input data, images with height and width, 3D convolution operates on 3D input data, videos with height, width, and time in it. So the key concept involved in the 3D convolution are kernel, strides, and padding. So in 2D convolution, the kernel is 2D matrix that slides over the image. In 3D convolution, the kernel is a 3D volume that slides over the input volume. And in strides, stride in 3D convolution determines the number of steps the filter moves in each of three dimensions, height, width, and depth. Padding, in another way, is similar to 2D convolution. Padding can be applied to ensure the output volume retains certain spatial dimension in it. So, so the input volume to the 3D convolution, like a video can be represented using a 4D tensor. So one represent the number of frames, then the height, then the width, and the number of channels in it. The number of channel over here is one because we are using grayscale images in our dataset. The 3D convolution operation works in a way that the 3D convolution layer applies a 3D filter that spans across the time, the depth, as well as the spatial dimension, height and width. For example, here we are using a 3 cross 3 cross 3 filter, and that will convolve over a block of 3 frames, considering this as 3 cross 3 spatial region with each frame. And feature is extracted. 3D convolution extract spatio-temporal features by capturing both the spatial information and the temporal information in that. So this is what the word eye view of our model. So we're using this UNET, and first of all, the image is given to us, and we'll pass it through several 3D convolution layer, and then we max spool it, and then again we do the convolution and then the max spooling. And basically, what we are given is that from t number of frames, the value of t that we have taken is 50. We randomly mask some images of it, and the masking is done like we randomly mask some portion of an image in a way that so that we can learn what how model is predicting those masked body parts. So that model will learn this thing called what is there in a video to for a walking action. Now, at the end of the encoder, we are calculating triplet and cross entropy loss. So first of all, we are training our encoder and then the whole model. So encoder is trained with the triplet loss and cross entropy loss, and after that, the whole model is trained with the efficient embedding that we get from these triplet and cross entropy loss. We are using mean squared error to train our whole model. So once we get these video embeddings, we try to reconstruct a particular frame from it, and which basically involve up convolution and then crop and concatenating. We are using 2 cross 2 transpose convolution in this. After the decoder had reconstructed image, we basically calculate this regression loss with a ground truth. And one thing that we are doing over here is the ground truth will not contain any mask frames. It's the original photo that, or frames that we have given. So in that way, our model will train. So the triplet loss that we have gathered from the training of the encoder is shown as below. So we can start it from something somewhere like 12 or something, and then the model will come to 2. The combined loss will be converged to 1, and so on. So what is triplet loss? Triplet loss is a function which is commonly used in machine learning, particularly in facial recognition or image similarity, to basically improve the performance of embedding models. So it works by training the model to minimize the distance between an anchor and a positive example, which belongs to the same class or as the anchor, while maximizing the distance between the anchor and the negative example, which belongs to a different class. The loss is defined for a triplet of images, an anchor, a positive, and a negative. The goal is to ensure that the anchor positive distance is smaller than the anchor negative distance by a specified margin that we have given, thus creating a well-clustered representation for similar items and distinct representation for dissimilar items. This helps the model to learn discriminative features that are crucial for tasks such as face verification. And here we are using on a video, we are learning the different gate features in it. Then we are using the cross entropy loss. So cross entropy loss, also known as log loss, it's used in classification tasks to measure the difference between the predicted probability distribution and the true distribution. So it's particularly effective for models that output probabilities, such as those using softmax activation in their final layer. So the loss quantifies the performance of a classification model whose output is the probability between like 0 and 1. So it is defined like minus negative of t log f of s1, like that. That formula is given to you. So basically, we are minimizing the cross entropy loss. So what it encourages that the model it encourages the model to predict the probabilities that are close to the true class levels, thereby improving its accuracy and reliability. So this is an encoder path of our model. So we basically giving a number of frames, and some of these frames are randomly masked, and the masking is like a particular body part is masked in that. So we basically pass these to our encoder. So each frame is passed so that embedding get created, and out of this 50, we like concatenate those to create a stack of embeddings. Then we calculate these split loss and cross entropy loss, and then we combine and then we backpropagate accordingly. So the input to this encoder looks like this. This is the shape of our tensor that we have. So 50 will represent the batch size, and the another 50 will represent the number of frames we have, and then this one represent the channels. Here we have a grayscale image, so it's like 1, and then we have the 64,64 to represent the image size. Accuracy and reliability. This is the decoder path of our model. So at the end of the encoder, we got a stack of embeddings. Then we like take one embedding from it, and then we pass it to a decoder. Decoder will try to reconstruct what is given actually at the input of the encoder. So it will once the decoder will calculate that, we first of all found the uh, MSE loss from it. So basically, we are comparing ground truth with the reconstructed image that we have figured out from the decoder. So yeah, uh, reconstruction of the video and MSE loss for the whole network. So these are like reconstructs MSE loss that we have gathered. So we train a lot, and we come from like 12 or something to this one value, and this is what a reconstructed video looks like. So like this is representing number of frames, and those number of frames particularly represent a particular video of a particular walking style. So that's what we have gathered. uh, Now we ask like why we have masked, and what's the uh, theory behind that. So it's basically like help us in ground truth comparison efficiently. So the model uses this original unmasked frames as a ground truth for training. So it helps in that. And uh, and in between the UNET, we have used this positional encoding and frame embedding. So frame embedding basically captures essential gate features in compact form and enhancing the recognition accuracy. And positional encoding maintains the temporal order of frames and improving the model's ability to predict and reconstruct the mask frames. So thank you. Let's do a thorough uh, deep dive of the code that we have written. Let's do a deep go through of the code that we have written. So first of all, I use this down utility by Google to just fetch the data from the brand. So I stored my PCIe dataset on this link, and when I like run this cell, then I'm able to download my dataset. It's actually a pickle file. I pre-processed it. So as you can see over here, this is the zip file that we have. Then I unzip this pickle file, and then I clone my repository where I have written the code. So this is like the clone folders repository appear to us, and I just moved that to my base folder called Kaggle working, and then I removed the PS1. So this is what this snippet is doing. Then I already trained my encoder, so I stored that those as a checkpoint, and I uploaded that to my Google Drive, so it's available over here. As you can see, this is what I've downloaded, model checkpoint PTH of the best efficient like weights that I have for the encoder. So yeah, let's come to the code. This data set class will represent the data. So what it actually do is like uh, it creates for each frame, it creates the label, the type, and the view associated with that. By like first of all, it relating all to the this information. It basically contains like the store the file path. So we create these three list and store our different uh, labels and types and views in it. And then we return it. So like each have some len function and the loader function. So that's what it is written over here. It's like reading this pickle file in the read code and then loading it and then running this logic, storing it and then returning the item from here. Like each item will return from this. Okay, and yeah, so this is like getting all the label that we have. For that we have written this. And for like parsing, if I'm basically using a dictionary to share like from where my date the root is presented. So for that, this is like the path of my pickle folder that I have created. So it's over here. So that's what it is written over here. And there's something called this JSON file. This JSON file will mention like how many IDs that I need for training and how many IDs that I need for the testing purpose. And this number of workers represent like number of processes that we'll create for that. And then this is the like the name of the dataset that we have. So this is what this code will do. So yeah, you run this and then we create this dataset object. So it contains the dataset class. Now next we'll have to like create a loader of it to just like iterate over the data that we have. For that we are using this collate function. This collate function defines like it's basically process a batch of data sample uh, for like we have this time series data. For that we basically wrote this collate function. So this class will basically provide different methods for those sequencing depending on the configuration that we provided in the dictionary. So if we see just the constructor of it, it requires label set and the sample configuration. Sample configuration is like the dictionary that I provided. It will be mentioned below. I will just show in further. So basically this sample config, it's a dictionary, and then this label set is like a list of possible labels for the data samples that we have. Then we have like this. What we are doing is we are parsing. So according to this sample type, okay, what is the sample that we are using, like fixed or unfixed, according to that, and then we basically do the validation. So validation is performed according to the sample type. After that, over here, like we have done the validation and all. So we have this call method. So what it's actually doing is, first of all, like it initializes our batch. So it determines the batch size and the number of feature in each sample, and then initializes the list to hold the sequences that we have. Like we are basically storing the sequence as a batch. Then what is there in the labels, then what is there in the types, and what is there in the views. So these are initialized over here. Then we iterate over the batch, and then we store like this over here. And then we also store the global count, like what we have. Now we have this function called sample frames. So now we have this sample frames function. So what it will do, basically we are using it for sampling the frames. So we have this called fixed or unfixed. So fixed is like sample a fixed number of frames. Unfixed is like it's not mentioned that how many frames that we want to sample. Then we have something also called the ordered and unordered. So that is like we want order particular order like that. So yeah, and after that, uh, for each sequence, this sample frame, what it's actually doing is for each sequence in the batch to obtain the sample frame, this is called, right. For that it's actually called. And then over here, like we are basically batch formatting. So if fixed is given, like then we convert the list of frames into a numpy array, and then we are storing these sequence and then frames in that this, right. Now for like I created this sample configuration. So it basically we are using 50 frames, and then we are skipping like 4 frames that we are sampling, and then we have used fixed order, and then for that we are using for sampling we are using a triplet sampler. So we have written some sort of like utility function. So just to check like whether the arguments that are provided are valid or not, and then we just wanted to like take from the source, if this is the name that we provided, then what should be like there in this source. For that we just like call this function simple, like iterating over the dictionary. And here we like initialize these torch processes. Localhost. Okay. Then yeah, here comes the triplet sampler, which is important. So okay, so the triplet sample is like this is the constructor of it. So it takes the data set that you created earlier, and the batch size and the batch double. So these things will be used, like batch double is true I mentioned, and then batch size and the type we are using the triplet sampler. So these things are passed, and then so the data set is this. We are using this. We are sampling it from here, sample data set. Then we have batch size. Okay, so batch size is basically a tuple p comma k, where p is basically the number of classes, or I would say the person IDs that is given to us in KCRB, and then k is the number of like samples per class. Okay, how many samples are there per class that we have chosen. Okay, so that's what we have done over here. Then this is like the iterate function. So first of all, like we get like PID randomly. It's basically randomly samples p unique class IDs from the dataset. So this thing will do that. So we create a sample indices also to store the indexes of those. And yeah, first of all, this suppling will work. So we mentioned that it would be true. So this will be true, and then this will get executed. So on based on that, batch will get prepared. So batch will get prepared, like ensure the what is the batch size, and according to the world size that we have mentioned over here on top. So according to that, this will get created, and this is to calculate the length of the data set. It's like a utility function. So yeah, so here we basically create the sampler. Then according to that, the dictionary we use that, and then triplet sampler got initialized. So then I create like the loader to load the data. So yeah, if I print it, then okay, just a second, I haven't run the previous codes. So okay. So let me run the code. Data set gets created, and then so this is where like we are storing the train loader of ours. Then we have these couple of PyTorch functions just to like initialize different processes. Uh, and then this is where like we have defined the class loss functions. I already declared below, so I will take these there. Like I will explain these over there. So yeah, and this is like some sort of common function that we have created, like different data structure that we are using in this. So for that, like I take what we have used over here. So these codes are taken from the framework that is given to us by our mentor to efficiently like maybe we have to integrate our model into that. So that's why we are using these over here. So these are like couple of utility functions that we are using. So that's not important here. Main focus was to on the model. So just a second. So this is another function that we have created called add mask. So it basically takes an image and then try to create a mask, like basically np.zeros of that shape, and then it so our image size that we are using is 64 cross 64. So we basically take like 16 comma 16 mask and then we randomly assign onto different positions by using this random and so on. So we are doing all of this in this input pre-treatment function. So I declared this two function without mask and mask for our use case. So in this one will create mask. So basically these inputs are passed, and then over here we are basically storing the different images that we have in a particular batch, and then here we have labels, then we have types, and then here we have views, and then the length of the sequence. So what we have done is I just taken this into another variable, and then basically on this length I just do masking on some four randomly. I pick four frames and then I mask those over here, like running this for loop. This will add those masks, and then again I just update my badge over here according to this. Then according to the transform that we are given, those dictionary values will come over here. So what? So it like basically convert according to the different data types like long and int, so that competition would happen in a proper way. And at the end, it will return the inputs, labels, tags, and views, and this tuple will get returned. So whenever we iterate over our train loader, the input labels, int types, views, these things will come to us. So this is like I written whenever we clear like one or two processes of Python, then in order to kill those, we have done that. So yeah, we don't have any. So this like I get this assessment error. So yeah. Okay. Now let's come to our main part, like the model that we have created. So yeah, so this is the code for that. So basically, first of all, like we have taken the CUDA and like we print the device then. So we basically have created these class for the frame embedding in a for our model and the positional encoding for our model. So we have defined these convolution 3D convolution blocks over here. So basically, we have two convolution, just like we have mentioned in our gate recognition over here. Like we use two convolution. So that's what is happening over here. And then after that we basically apply the ReLU for at the output of that. For that it is mentioned. So in the forward pass, first of all we apply this convolution, and then we do the ReLU. Then again whatever is the output of that, again convolution will happen, and then ReLU is applied, and then it will be updated to X. And this is what is happening in our convolution 3D block. So each of this is like we have different encoder blocks in it, 1 2 3 and so on. It is converting. So we have so this is like encoder block. So what encoder block have is the convolution block and the downsampling layer. So for downsampling, we are using this again we are convolution using this convolution. So but we declared this structure like this convolution 3D block for the convolution block and the downsampling block. In the forward method, whatever be the input that is given to us, first of all it is like convolution will happen, and then we are like max pooling it. For that this is using, and then we return both of these. And here we have the decoder block. So decoder will like upscale our input that is given to us. So it's contained like we have defined like in channels and out channels. So it have this convolution block and the upsampling block. We are using this con transpose 3D to like upsample. So this is the forward method. So whatever be the x we have, we also have the skip connection into it. So that's what we have. So basically x will come, and then we apply this convolution, then when we upsample, and then we basically concatenate the input with the skip connection with this dimension one as for a tensor, and then we return. So this is our decoder block. Now let's come on to our model. So UNET will have like first of all we have different encoders in it, basically converting bigger dimension to the lower dimension, and then we have the decoder blocks. So that is what written over here. So in the init, so first of all we like I mentioned like what will be the frame embedding dimension. This is like hard coding. We'll pass it again. So first of all, this constructor will call and super of it. So NN module constructor will call and it will initialize. And we define these encoders. So for we have like one channel, and then 64 image will get passed into it. This one. So uh, this will be the first encoder. Then then we have the second encoder. So whatever be the output of it, it will be passed into this. So it's like 64. The output is 128, and then 128 to 256, and then 256 to 512. We haven't done like 102 for it because it's taking a lot of time to for training. So we just kept like 512, and then again we are using this 512 to upsample. So that's what we have done. Now we have also added this global average pooling layer for um, like basically generating embedding efficiently. For that we have also added this structure. Then we have the decoder blocks. So the output of this will fed into the decoder, and then it will like upsample the image. So that's what is happening over here. 512 to 256, and 512 to 128, and then 128 to 61, and so on. And this is our, we are also like storing the decoder output in this final convolution. So again, we are convolution at the end. So to get our desired shape, our desired shape is like I will mention in the further course. So this is like the forward method of our unit. So we are passing the input, then the frame indices for the position encoding, and then the encoder only. This is like we are training in a way like first we are training the encoder, then the whole network. So whenever we pass the encoder only as true, then we are only training the encoder. So how it's happening is first of all like input will be passed to encoder, then we get these two output, then to the second encoder, the third encoder, and the fourth encoder, and then we got these, and then embedding get created, and yeah, we are squeezing according to and squeezing and all we are doing that for our model shape. Then if this is like false, then decoder will run. If it's not, then we basically come over here and then return the embedding. So just for to train our encoder and to calculate the triplet loss and cross entropy. If it's false, then this will get executed and then decoder will get executed and then we at the end return the output of that decoder. So let's come to the triplet loss. So this is our triplet loss code. So where we are passing the margin and the loss weight term, and then we are storing those in the instance variables in the constructor of it. Then we have this forward method. So in the forward method, first of all, whatever the embedding data passed to it, we are squeezing it, and then we store the size of that. And then this thing what it's actually doing is pairwise distance. So a matrix containing the pairwise Euclidean distance between the embeddings got created from this. And after that, we are like okay, so this is defined over here. So what's actually happening over here is it's computing the pairwise Euclidean distance between all the embeddings. So it basically do the dot product and compute the matrix. So square sum is like it extract the square sum of the embeddings. Then the distance matrix is calculating using the Euclidean formula, and we apply this f dot value over here. Then and then we do the square root, and then we return the distance matrix, and then it's stored over here. Then we are calculating this triplet loss using this method. So it's defined over here. So what's it actually doing is first of all like we have this. It converts a label of numpy array for easier like manipulation, and it's for this reason we are storing the labels, and then we are running this for loop. So we are it looks over all possible triplets like I, J, and K, where I is basically the anchor and J is the positive example, the same level as the anchor, but not the same instance. That's what we are ensuring like this, and then we have this K, which is basically the negative sample. It's actually different from the anchor result. Okay, and then if there is no valid triplet available, then we basically return the null over here. Apart from that, we are storing the triplets over here like this. Okay, and then we are returning these triplets uh, according to this distance matrix that we created. So yeah, and where am I? Yeah, over here. So after this, this is what we will get executed. So AP distance is basically the distance between the anchor and the positive. AN is basically the distance between the anchor and the negative. And triplet loss is like it basically computes the triplet loss using the formula this that is mentioned over here. Max of like 0 comma AP minus AN plus some sort of margin here. So that is what is mentioned over here. So now we are like calculated the loss, and we have this loss vector. So then we return the loss and the information in it. So yeah, this is all about the triplet loss. Let's come to the entropy. This is where our gross entropy loss is defined. So first of all, these parameters are passed into it, and in the constructor we just basically like store those into our instance variables. So we have this forward method in it. So the logics are passed like the embeddings and then the labels of it. Then what's happening is first of all like we squeeze our input, and squeezing is like we remove the second dimension if it's of size one. This is like common when we are dealing with certain output shape of neural network. So that's what we are doing because we are not able to manipulate the data accordingly, the shape of the tangent that we are given. So then we are like converting it to log data type in PyTorch, and then if like the self dot label dot smooth, then we are like calculating this. And then if not, then we are using this. So what is happening over here is so these representation are already there in our PyTorch. So what we are doing over here is we are scaling the embeddings by a specified factor before computing the loss. So that's what is happening. If this log dot accuracy is true, then we are also calculating the accuracy. So it basically calculates the prediction accuracy. So over here, it gets the predicted class by finding the index with the maximum logic. So Argmax is used for that. And then the second is like over here, it compares the prediction with the true labels to the calculate accuracy, and then we like return the loss according to that. So this is what these losses that we have used. Now here comes to the training loop of the encoder. So let me do this. Yeah, and then here basically while we are loading the data, so we are also adding the padding to just make sure we are passing 64 plus 64 image. So here we have defined initializer model. So I already like trained my encoder very well. So over here those checkpoints are there. So I loaded those, and then here like, first of all I initialize the triplet loss function and the cross entropy loss function with margin as to like over here I'm using. Uh, then I just use this optimizer header, and then I define like number of epochs. Then according to number of epochs, I first of all I'm using this total loss variable. So I'm iterating over each batch in the loader. Then I call this input pre-treatment, which will give me a random masked images. So those are stored over here in this input. So first of all, I add those padding so that it will convert it into 64 cross 64. Then I unsqueeze it accordingly to like, convert the tensor into particular shape. Then I load these to my CUDA device. Then for each batch, I want to like stack my embeddings as mentioned over here. So this is this stacking. So for that, I create this like variable. So first of all, since I'm training my encoder, so I pass this as true, and then this will like initialize it. Then we are also like I created this batch label. This also contains the labels, and it also like concatenation also happen for this batch. So I iterate over this these input that is given to me, and okay, it's of no use. Then first of all, like padded, this is the input. So basically, first I can squeeze it again for some shape kind of stuff. Then for calculating this positional encoding and frame embedding, I create this frame indices variable for that. Then I pass this as input to my model and to for training my encoder, and then these are passed for positional encoding and frame embedding. And according to that, I'll get embedding, and then I can concatenating those to create a stack for batch embedding. So this is how batch embeddings get created, and then I pass those batch embeddings into my triplet loss function and the labels, and triplet loss will get calculated. Same for the cross loss. Then I combine and then back propagate and optimization happen over here. Then we are printing the loss. So since we have already trained a model very well, so we like 2 point something of like retrain it. Oh, I haven't trained the previous cells. Just a sec. So as you can see, we have this losses coming to us. So this is how the encoder is get trained. Once we have trained our encoder, then we go for the training for our whole network with the MSE loss. So basically, we have this again, this model I created. Like the previous one model is written. I think different. Difference. Say, difference is this a training loop. So this is another function that I have used like just to output like create the images from the tensor that we have. So for that we have used this like using the matplotlib and so and all. So first of all, this model get initialized. So fully trained model is already there. So I have stored over here for that. This will be this will like load that model. Will download it. So yeah, so optimizer get created, number of epochs get created, and then we iterate over a loader, and then we get these inputs. Then uh, again, so when I'm calculating this MSE loss, so I need the for ground truth, I don't need the mask images for that. So I call that this input speed treatment without mask. So this get called, and we do the same pre-processing stuff that we have done earlier, and same I've done for the ground truth. Then I created this each video loss, like for one video, what is the loss? So this is passed over here model, and then we calculate the embedding, uh, the output of the decoder. So we slice to those accordingly, and then we calculate the MSE loss over it, and then we backtrack, and then according to that, our model get trained. So let me connect. Before that, we whatever this model will predict this model predict embedding. So this contain a particular loss. So I called this one, I call this function to like check what is the output of the decoder. So it's stored over here. We are passing this false for training the decoder. So this will contain my output of the reconstructed images from the encoder. So yeah, this will get created over here. So let me run it. As you can see, this is what decoder is uh, reconstructing. So frame 1 to like frame 49 is a walking style of a particular person from year to year. Like, so this is what it's actually predicting. Yeah. And then we have at the end we are training this classification head model. So it's basically contain a linear layer. Basically, whenever I get a test check, then first of all I pass that to the same pre-processing layers that we have passed, and after that I first of all pass that until the encoder, so to get my embedding, and then I use those embedding with the label to find the loss, and then for that I'm training this model. So yeah, that's what we're doing over here. So it use the cross entropy loss because we are classifying the embedding with different labels we have. So this is the same code we have. Uh, since we are doing the training of encoder only, so this will predict the embedding of the encoder, and those are concatenated, and once those are concatenated, we will pass that to our classification head model, the simple linear fully connected layer that we have created, and then it will create the its own like a tensor, which is basically a size like 50, 74, 50 for the number of images in a particular batch, and 74 is like the number of training samples that we have, and then we calculate the loss, and according to that we have export propagating and data. So yeah, this is all about our code.